So the next talk is by Professor Badi Sidri, and he will talk about non-commutative geometry, matrix quantum mechanics, and the correspondence between them.
Yes.
Professor Idri, please.
Thanks very much. Sorry for this delay. So do you hear me? Shall I start? Yes. So I would like to talk briefly about quantum mechanics and the correspondence between quantum mechanics and non-commutative geometry. So I take as an example quantitative space-time in two dimensions. We will quantize ADS2, which try to write down a matrix model which will capture the essential features of non-commutative ADS2. And then we will describe the phase diagram and try to see if we have an information loss problem on ADS2. The second bit, I have time, I will try to discuss the quantum mechanical dual, so this theory. And then I will conclude with a brief discussion of the correspondence between non-commutative ADS2 and the quantum mechanics of the AFF, the so-called conformal quantum mechanics. So we know that in Euclidean dimensions, in two Euclidean dimensions, we have two positive curvature spaces, S2, and the pseudosphere, H2. The pseudosphere is our Euclidean ADS2. So we are mostly interested in Euclidean ADS2, but so the discussion will be more rigorous. And of course, within ADS2 or the pseudosphere is related to the on-identity effect by standard width rotation. The quantization of the sphere is known to be given by the fuzzy sphere. The quantization of the pseudosphere is given by the non-commutative pseudosphere H2 theta. They have the same isometry groups as the commutative spaces. The fuzzy sphere is known to be unstable, so we know this. So the fuzzy sphere is unstable, and it evaporates in the phase transition to an Euclidean Young-Mills phase. This is a geometrical phase transition, which we also call emergent geometry. This is a known part. We will also show that non-commutative pseudosphere or Euclidean ADS2 is also unstable and can evaporate in a phase transition to a Lorentzian Young-Mills model. This is also an emergent geometry transition. However, the non-commutative pseudosphere can also sustain black hole configurations, both including dilatonship. We need to include dilatonship, which we will do in a short moment. This configuration can suffer collapse in the form of the so-called information loss problem. This for us is precisely a gravitational phase transition or emergent gravity. The fact that we have the possibility of a dilaton field, this will present itself in our description as an emergent gravity or emergent gravitational phase. Also, we will show that the emergent gravity transition is actually the inverse process of the gravitational information loss problem. So our understanding of the information loss problem is the fact that it is the inverse process of this emergent gravity. So we have an emergent geometry that is the emergence of the pseudosphere from a Young-Mills model, but we also have an emergent gravity that is the emergence of a black hole, of an ADS2 black hole configuration from pure ADS2. And this transition, the inverse of this transition is our information loss process. So all these geometrical and gravitational information loss processes are strictly speaking unitary processes. They are all occurring in path integral quantization, of Young-Mills matrix models of the IKKT type. So they are unitary process. So we have, in summary, the following phase transition or the following phases: a gravitational phase, in which we have a dilaton field. So the dilaton field acquires an expectation value, and the gauge field acquires also an expectation value. A geometrical phase in which the gauge field only condenses, the dilaton field is zero, and we have a Young-Mills phase in which none of the fields condense. All of them have zero expectation value. These are the three phases of that we have in this Young-Mills mesh model, which I will write shortly. And and they are, as I said, unitary processes. These are ordinary phase transitions. We can also specify the degree. So they are unitary processes in path and error quantization. So clearly, or what I explained is that we have really no information loss problem in this non-commutative model. In the commutative limit of these Young-Mills mesh model, what we have, the mesh description becomes unavailable, and we are back to the usual descriptions of the black hole evaporation process, where seemingly information is lost. This is the main method of this talk. So we have really in this description of in our description of non-commutative black holes, non-commutative ADS2 black holes, we have an instability. We have really an emergent gravity phase transition, but we do not really have an information loss problem because it is simply a unitary process. Let me start by giving a brief discussion of the non-commutative sphere or non-commutative Euclidean ADS2. So this is the quantization of symplectic space, symplectic manifold. It has a symplectic structure which can be quantized in the usual way. And the answer is a non-commutative space given by certain irreducible representations of the group XO12, which is the group isometry group of H2. So the isometry equation 2 gives me ADS2 as embedded in 3-dimensional in Minkowski space of 3-dimensional size. So this is our ADS2. And the quantization of this space simply reproduces the usual, irreducible representation of SO1. Clearly, this surface has an SO1 isometry group. So the relevant for Euclidean. The pseudosphere or Euclidean ADS2 is really given by this embedding condition, but also is given by these commutations correlations. The x hat are the coordinate operators on ADS2. The structure constants are precisely the structure constants of the group SO12. Kappa is here, this number is the deformation parameter. The irreducible representations we are talking about, these Ka are given by the irreducible representation of SO12 given by the discrete series. So these are standard representations which we recover for Euclidean ADS2. For Lorentzian ADS2, we will obtain the continuous series. But the difference is really at this stage, difference is really only in the type of representation which we cover. However, for us, non-commutative ADS2 is obtained by a weak rotation of Euclidean ADS2. We can really understand the quantization of Euclidean space. Quantization of a Lorentzian space is really troublesome, and it's really only a formal. Really. So this is the structure. This is our non-commutative ADS2 given by equation 3. And the irreducible representations of the discrete series of SO1. Just word on the commutative limit. We can relate the deformation parameter kappa with the radius of the ADS2 and also the pseudo-spin quantum number K. So the group SO12 comes with the irreducible representation given by the discrete series of the group S412 comes with a pseudo-string quantum number, which is here denoted by K. So this is the relation which relates the main parameters of the model. So the radius, the deformation parameter, and the pseudo-string quantum number. So the commutative limit really is given by kappa goes to 0 or K goes to NP. This is exactly what happens also on the public here. So this is the commutative limit. Now we write the gauge theory. So the idea is simply to replace this coordinate operator and simply replace these coordinate operators with some gauge covariant operator. So we introduce a UN gauge symmetry by substituting the coordinate operator by some matrix EA, which transforms unitarily, which transforms under UN gauge transformation in the usual way. So I write a field strength. This, if I replace the A by the coordinate operator, I get 0. This is exactly this statement. This is exactly this commutation relation. However, now I replace this configuration by pure gauge configuration, which are given by U F hat E that. Then I include non-trivial field configuration by adding some connection, kappa A, and I write an action which is given by the usual Young action. I take here a complete square, which is I take F squared, where F is the strength, and I write this matrix model. This is matrix model I would like to study. The parameters here are given by this alpha, which is the parameter chance and return. This is the relative deformation parameter as in the coordinate. But we have also some master data. I will not discuss so I can discuss actually the phase diagram of this model in alpha plane, but really what interests us is the data equals 0 value. That is sufficient to obtain the flavor of what's going on. So I simply go directly to so I simply set this mass parameter beta to 0, and I study the model. What I find that there is there is only a single parameter, which is this alpha. Here, chance time occurs. This will play the role of the inverse temperature. The inverse temperature, the metric temperature, not the half-in temperature. So T is equal to 1 over alpha to the 4 is the temperature of this model. As we increase this temperature, the non-commutative pseudosphere, the leading ABS2, evaporates at some critical value alpha tilde star to a Young-Mills metric phase. The Young-Mills metric phase has no background geometry structure at this stage. I can say more on this if I have time, but for the time being, there is no background geometry structure here in the Young-Mills metric phase. So we have a phase transition at some critical point alpha tilde star between a pseudosphere phase and a Young-Mills. This is the essential behavior. The order parameter here, I took it to be precisely chance parameter, nothing more, just a chance parameter. If I now would like to study this model in the alpha beta plane, I will find a picture like this. This is actually the phase diagram on the fuzzy sphere, but this is precisely the phase diagram. This is what I conjecture here is that this is precisely the phase diagram on Euclidean ADS2 on the pseudosphere. So there will be a pseudosphere phase, and there will be a mesh phase, and there is a line, critical line, coexistence line between them, which will saturate at some value, which is precisely also 2 over 9 in both models. So this is the picture in general, and the order parameter can be taken to be the chance time. It is non-zero in the pseudosphere phase, and it is 0 in the Young-Mills phase. It is actually the term responsible for the emergent zone, for the condensation of the zone. Now I would like to add black hole. I would like to add ADS to black hole. So I need to add a Delacourt field. So there is no way around it. So we cannot have stable configuration in 2 dimensions stable black hole configuration is still in 2 dimensions without a dilaton field. So I will take back the signature. As I said, the discrete series relative this is replaced by the continuous series. This is now we are already now talking about non-commutative Lorentzian ADS2. This goal, I write this goal and I simply say what is our goal. I would like to write down non-commutative ADS2. Non-commutative dilaton field. I would like to write down 4-dimensional using a 4-dimensional Young matrix model. Remember, the Young matrix model is 3 dimensions. Now I will have a 4-dimensional I will have an extra. So did you hear me about the goals now? I would like to write.
Oh, it's a bit loud.
I would like to write non-commutative black hole solutions. This will include the dilaton field. I would like to write a 4-dimensional Young-Mills matrix model, and I would like to study the phase diagram of this 4-dimensional Young-Mills model, of this 4-dimensional Young-Mills matrix model, and it will include 3 phases: a gravitational phase, a Young-Mills phase, and a geometrical phase. The evaporation of the ADS2 black hole will present itself as a phase transition from the gravitational phase to the geometric phase. And there will be no information loss problem because the whole process is unitary. Do you hear me now? Hello? Do you hear me?
We can hear you better.
Thank you. So I would like to do that, if you don't mind. I just remind you about the black hole. So I would like to consider here the black hole, ADS2 black hole. So I write in equation 10 the usual pure ADS2 Poincare coordinates. Then I write the same space in Schwarzschild coordinates. They're equivalent. There is no black hole solution as such, but we notice that this metric equation 12, which is the ADS2 black hole in Schwarzschild coordinate, actually describes an ADS2 black hole solution if we include a dilaton field. If you join this metric equation 12, if I join this equation 12, which gives me the metric of ADS2 spacetime in Schwarzschild coordinate, I join it with the dilaton field given but precisely by this configuration, I get an ADS2 black hole. This is a solution of the celebrated Jacquiev Teitel-Bohm action. Everybody knows that. So this is our configuration. This is our ADS2 black hole configuration. Now I write it again here in this slide. So this is equation 15 is the pure ADS2. Equation 16 is the ADS2 black hole. The horizon is A by lambda, where A is this parameter. Lambda is the inverse radius. Lambda is 1 over R, where R is the radius of ADS2. And the mass and temperature of this configuration are listed in equation 17. They can be computed in the standard fashion. Now I would like to write the non-commutative configuration, the analog of this configuration in non-commutative geometry. So what I do, I simply rewrite the dilaton field in terms of the embedding coordinate. I find that it is precisely proportional to x1. X1, remember, the coordinates of ADS2, the embedding coordinates of ADS2 are x0, x1, and x2. So phi is proportional to x1, 2p. T here is the Hawking temperature. It is not the matrix temperature. Now I quantize this by simply replacing everything by operator in the appropriate Hilbert spaces. That's a standard thing. So we simply replace x1 by the coordinate operator, x hat 1, and I get the non-commutative dilaton field. This dilaton field satisfies these commutation relations. You can simply use the commutation relations of non-commutative ADS2 to find these equations that needs to be satisfied by the dilaton field or the dilaton field operator. From these equations, I can even describe the dilaton field using the following equation. This is a constraint on the dilaton field that needs to be satisfied. Script K is the non-commutative derivation. It's given by the exterior derivative, the commutator with the SO12 generators. As it turns out, this is precisely the constraint satisfied by the commutative dilaton field. The dilaton field in the Jaquiev Teitelbaum model can be rewritten in terms of a nonlinear sigma model. This is a known result. I can rewrite the whole theory as a nonlinear sigma model. This is equation 24, where the ADM mass M is given by this constraint. So it's given by this constraint. Now, the commutative limit of our constraint is precisely this constraint. That is the statement. So we have really capturing the description of a non-commutative ADS2 black hole. It has the correct commutative limit. It has the correct commutative limit as a nonlinear sigma model, which is equivalent to the usual Jaquiev Teitelbaum model. Now, once we have reached this point, we are more confident that our description of the dilaton field is indeed given by these commutation relations. Now, I would like to rewrite these commutation relations in a way that allows me to write a Young-Mills matrix model for which the classical solutions are given by this dilaton field plus the non-commutative ADS2. So I rewrite these commutation relations as a field strength, as in equation 26. So I simply rewrote it. So the extra structure constants are given explicitly in blue. Recall that the field strength which corresponded to the coordinate operators on ADS2 is given in equation 27. I put it 26 and 27. I get a field strength in 4 dimensions. 27 is a field strength in 3 dimensions. Really. So I get a field strength in 4 dimensions where the dilaton field is the coordinate operator number 3. So x hat 3 is identified with the dilaton field phi hat. So this is the field strength. Directly I can generalize to gauge theory in the usual way, and I write a gauge action, and the gauge action will have these terms in it. The most important, this is the 4-dimensional Young-Mills matrix action. This is our gauge action. It describes quantum gravitational fluctuations about the non-commutative ADS2 black hole. The classical solution of this matrix model is given by the non-commutative ADS2 black hole. That's the statement. This matrix model includes two Chern-Simon terms. One responsible for the emergence of the geometry of ADS2. The other one, this one, is actually responsible for the condensation of the dilaton field. So there are 2 competing Chern-Simon terms, which causes the system to suffer 2 different phase transitions, a gravitational one and a geometric one. Let's simplify this model by simply putting the beta term to 0. I get this term here, and also simplify the Chern-Simon. This is the first one. This is the one responsible for the emergence of the ADS2 geometry. The second one is this one. This is the one responsible for the condensation of the dilaton field. D3 is the dilaton field, recall our notation. Now we have, as before, 2 phases. So I can simply describe the phase structure. I can go through that. So the first Chern-Simon, this one, is responsible for the condensation of the non-commutative ADS2. This is emergent geometry. The second Chern-Simon, as I said, is responsible for the stability of the non-commutative ADS2 black hole, which means the condensation of the dilaton field. So this is an emergent gravity, and the inverse process is precisely the black hole evaporation process. So we have 2 critical points, alpha 1 and alpha 2, correspond to the vanishing of the 2 Chern-Simon's expectation values. So I take as order parameters these Chern-Simon's operators. So you have 3 phases. If I take alpha greater than the second critical value, alpha 2 critical, So we'll have the so-called black hole phase or gravitational phase. In this phase, the dilaton field is proportional to d1, and d are given by the coordinate operators x hat r. This is a gravitational phase in which the non-commutative ADS2 black hole is stable. If I take alpha between the second and the first critical point, the second Chern-Simons terms effectively vanishes, whereas the first one does not. So we have the dilaton field should condense around 0, whereas the dA, the meshes dA still fluctuates about the non-commutative ADS2 space-time. So we have here pure ADS2 phase. This is geometric phase. If we keep increasing the temperature, the matrix temperature here, by the way, there are two temperatures here, the matrix temperature, which is inversely proportional to this alpha, and the Hawking temperature. So if we keep increasing the temperature, which means increasing alpha, decreasing, sorry, this is a mistake, decreasing alpha below alpha 1, the ADS2 background itself will evaporate and to something called the Yang-Mills matrix phase. All matrices fluctuate around 0. In summary, the Hawking process presents itself in this Yang-Mills matrix model as a phase transition from the gravitational phase to the geometric phase. This is the inverse process of the emergent gravity geometry, of the emergent gravity transition. At this stage, so this is what I wanted to say about the non-commutative black hole. If I still have time, I would like to say something about the theory at the boundary of non-commutative ADS2.
Professor Idri, only 5 minutes.
Can I still continue? Do I still have time?
Yeah, 5 minutes more.
5 minutes. Okay, so I'll just be quick then. I would like now to go to the boundary. So the boundary. I would like to go down to the boundary. So the boundary, the boundary of non-commutative. So the main statement is that the non-commutative. The main statement is that the non-commutative ADS2 is asymptotically ADS2. That's the main statement, which means it has the same boundary as the commutative ADS2. They have the same boundary, and more than that, we can, and therefore there can be so it is one-dimensional or the ordinary boundary. So there is a conformal boundary located at z equals 0 in the usual Poincare coordinates. This is the usual boundary, which we know. This is also the boundary of non-commutative ADS2 theta. So this is this is the region in which the dual conformal quantum mechanics resides. That's the principle. So I write this conformal quantum mechanics. So to take the boundary theory to be the usual DAFF quantum mechanics. There are, so I can write the generators responsible for, so the generators of this DAFF quantum mechanics. These are given in equations 35. These are the usual translations and scale transformations and special conformal transformations. And I can also realize them explicitly in terms of either so two remarks here are in order. First of all, this DAFF quantum mechanics does not include an SO12 invariant vacuum state. I don't have a state satisfied by this equation. And second of all, this quantum mechanics does not include primary operators in the usual sense. All I have are operators satisfying equation 42. Yet that is sufficient to reproduce all bulk operators. So the boundary operators, the boundary correlator operators computed using this quantum mechanics are precisely those computed in the bulk. So what we have, the only thing I have as vacuum, I don't have a vacuum annihilated by everything, by all operators. I do have only the lowest weight state. That's all I have. Also, I don't have primary operators in the usual sense. All I have are these coherent state kind of operators constructed here. and they satisfy this condition. So yet this data is sufficient to construct a state boundary correspondence. So, and this is given by the red line in this line here. So this DAFF quantum mechanics is really not exactly conformal. It is what I call quasi-conformal. In the same, this is in the same way that non-commutative ADS2 is not exactly conformal. It is quasi-conformal. It is only asymptotically ADS. So this is the idea of this correspondence between quantum mechanics from one side and ADS2 from the other side. So the quantum mechanics is really quasi-conformal. So it's only quasi-conformal. And the ADS2 in the bulk must also be quasi-ADS, quasi-conformal, which is given by ADS2 theta. Furthermore, the algebra of the quasi-primary operators on the boundary is exactly sub-algebra of ADS2. This is very important. So the algebra of the quasi-primary operator, which we have constructed, is a sub-algebra of ADS2. And the Laplacian operator on ADS2 has the same spectrum as the Laplacian operator on ADS2. So the non-commutative ADS2 and the commutative ADS2 share the same spectra. So all these things allows me to say that really what we should take as a bulk theory for this DAFF quantum mechanics is non-commutative ADS2 theta, not commutative ADS2 as it is usually done. This is my other main message. So this is summarized here in this picture. So the bulk is really given by the algebra of non-commutative ADS2 theta. The bulk is non-commutative ADS2 theta. The boundary is asymptotically ADS, so it is the same boundary. So there is a quantum mechanics living there. That quantum mechanic, if we take it to be the DAFF quantum mechanics, is really not exactly conformal. It is quasi-conformal. So it seems to me it is much more natural to say that this quantum mechanics, this DAFF quantum mechanics, is dual, or it is the dual theory of the non-commutative ADS2 theta. And I stop here and thank you very much for your understanding. Do you hear me?
Thank you, Professor Idri. We have question for one or at most two questions.
Thanks, Badis. Very nice to see you. This is Dinjo. I am wondering, is there any problem with the SU21 and the action that you're using being bounded from below?
That action, of course, is Lorentzian as it stands, even for the pseudosphere. So it needs a regularization.
Okay, all right.
Yes.
Sure.
Needs a regularization.
Okay.
As it stands, it is really, although we are talking about the pseudosphere, locally the pseudosphere is Euclidean, but the matrix model as it stands is Lorentzian. So it needs regularization.
I think you'll probably be okay in the strict Largen limit, because
yeah, it is okay in that strict Largen and limit in the pseudosphere phase.
Yes, in the neighborhood of the pseudosphere phase. Yes. Okay. Thanks.
Yes, no problem.
Right.
In the other phase, you cannot simply. It requires some weak rotation and things like that, and regularization. The whole thing requires actually a regularization because this is an infinite dimensional matrix model. Yes.
If there are no more questions, let's thank the speaker again. Before we conclude, let's thank all the speakers of this session.
Thank you very much.